Hey class, so here's another example problem for you. This one is going to deal with a collision that takes place in two dimensions. So we have to use conservation of energy, conservation of momentum in both the x and the y direction. So what we have going on here, as you can see, is there's this mass A that's 5 kilograms sliding along the ice, so we're assuming it's frictionless. We have an isolated system because of the ice. It's moving at 2 meters per second. It collides with this chunk B, which is 3 kilograms, and it bounces off at 1 meter per second at a 30-degree angle, and we're asked to figure out the magnitude and direction that ice chunk B is going to move after the collision. So, as I mentioned, since we have an isolated system and we have a collision, we need to make sure to use conservation of momentum. Now, some of you would see this, oh, they're bouncing off. Maybe it's an elastic collision. I could just use kinetic energy. That'd be way easier. But the thing is, we don't know for sure that it's elastic. Unless we're told, we do not know that it's elastic because you can have them bounce off and still have a partially inelastic collision. So we're going to use conservation of momentum, which means our initial momentum is equal to our final momentum, which means our initial momentum in the x direction is, I don't need the hat since we're doing the x direction there, is going to be equal to our final momentum in the x direction and our initial momentum in the y direction is going to be equal to our final momentum in the y direction. So to get this going, we're going to need to make sure we break everything down into x and y components. As far as the initial situation goes, it's quite easy. Velocity of block A initial in the x direction is just the 2 meters per second that we're given. Velocity of block B initial, I should just be consistent. Sometimes I use I and sometimes I use O for initial. So we'll go back to using O. Velocity of A initial in the x is 0. Velocity of B initial in the x is 0 meters per second since it's at rest. Velocity of A initial in the y is 0 meters per second, while velocity B initial in the y is also 0 meters per second. It's fun when your subscripts spell things like box and boy, as we see here. Pretty fun. All right, then velocity of A final in the x direction, well, that's going to be 1. It's at an angle of alpha times the cosine of our angle alpha, meters per second, and velocity of B final in the x direction is going to be 1 multiplied by the sine of alpha, meters per second, and then velocity of B final in the x, we don't know, and velocity of B final in the y, we don't know, and I just realized I made a typo. This is not B, right? This is A final in the y, so boy howdy. Okay, so we have velocity of A final in the x is 1 cosine, velocity of A final in the y is 1 sine alpha. So sorry about that. These are both A. So on this side, all of this is A, and all of these over here are B. And so it's the velocity of B final that we're trying to find, and we know that velocity of B final, the overall magnitude of its velocity, is just going to be the square root of velocity of B final in the x squared plus velocity of B final in the y squared. So you could break that up into components based on beta, but you don't need to necessarily, and the algebra might be easier without it, so I'm not going to go that route. So let's do conservation of momentum in the x direction. All right, so let's start with conservation of momentum in the x direction. So again, I'm going to write it all out in variable form, and then we can plug in just to show you the process. So initially, we would have mass A times velocity of A initial in the x plus mass B times velocity of B initial in the x, and that would be equal to mass A times velocity of A final in the x plus mass B times velocity of B final in the x. So you would have to do everything all written out as you can see here, but we have the added advantage that this is 0, so we can ignore that, and we want to solve for VB final. So VB final in the x, I'm going to skip a few algebra steps because you guys are getting good at algebra by now, should be equal to mass A times VA initial X, that's what we have here. I subtract this from both sides, so I have minus mass A times VA final X. And then I have to divide by this mass B here to get the velocity by itself. And so that should be my overall velocity B final in the X equation. So we can plug and chug. I could even factor out mass A here. So I have 5 kilograms multiplied by velocity of A initial in the X, which is 2 meters per second, minus 1 times the cosine of 30 meters per second, and divide all of that by the mass of B, which is 3 kilograms. And if I did my math and my algebra correctly, VB final in the X should come out to be approximately 1.89 meters per second. Boom. All right, sweet. So that's our X component. Now we need to move on to doing conservation of momentum in the Y. Maybe I'll switch colors to stay organized. So now we're going to be looking at momentum in the Y. So P initial in the Y equals P final in the Y. So again, I'm going to write it out in variable form so we stay clear on what's happening. So we have mass A, V initial A in the Y direction, plus mass B times VB initial in the Y equals mass A times velocity of A final in the Y, plus mass B times velocity of B final in the Y. It's a major subscript party here. So these are both 0, so that's a bonus. So our initial momentum is 0, which means our final momentum also equals 0, but we still need to solve. So we have 0 equals MA VA final in the Y plus MB VB final in the Y also. And so now we can solve for VB final. So VB final in the Y should be equal to MA times VA final in the Y divided by the mass of B. So we can solve. Let's plug in our numbers. Mass of A is 5 kilograms. VA final was 1 sine 30 meters per second. And then mass of B is 3. Oh, boy, howdy. I missed. I moved this to the other side, so this should be negative. Oh, that was close. But the mass is 3 kilograms. So if we solve, VB final in the Y should come out to be equal to negative 0.833 meters per second. Now we can find our final velocity and our angle. So VB final then, the magnitude is going to just be equal to the square root of 1.89 meters per second squared plus the negative 0.833 meters per second quantity squared. So we do the math and we find that the final velocity is 2.07 meters per second. Boom, most definitely box worthy. And then lastly, to find our angle, all right, we know that our angle beta is just going to be equal to the inverse tangent of the magnitude of VBY over VBX. So the magnitude of the Y component is just 0.833 meters per second, and the magnitude of the X component is just 1.89. Let me write that a little cleaner, 1.89 meters per second. And so if you solve, you should find that the angle is 24 degrees. So box worthy again, we have a final velocity of 2.07 meters per second, 24 degrees below the positive x-axis, which is how it's drawn, but we could write it if we want, below positive x-axis. And then lastly, we were asked, is this an elastic collision? If it's elastic, that means that your kinetic energy initial equals your kinetic energy final, right? So let's see whether or not that's true. Let's calculate each of those real quickly here. So kinetic energy initial is just going to be 1/2 MA VA initial squared plus 1/2 MB times VB initial squared. But VB starts at rest, so that's 0. So K initial then, if we plug in 1/2 5 times 2 squared, 1/2 5 times 4 gives us 10 joules of energy is what we start with. And then for the final, K final is 1/2 MA times VA final squared plus 1/2 MB times VB final squared. Plugging in again, VA final is 1, VB final is 2.07 meters per second, MA is 5, MB is 3. So if you plug and chug, you should find 8.93 joules as your final kinetic energy. So no, we do not have an elastic collision because we have kinetic energy being lost. So I hope that that helps. Let me know if you have any questions, and other than that, have a box-worthy day.